Thanks for tuning in. This is going to be a lecture about basic network routing concepts. My name is Professor J Patterson. Whenever you request a resource on the internet by using a URL or the internationalized version of a URL called an IRI, you're going to need to use many computers on the internet, kind of hidden from the requester, but that are all collaborating together in order to deliver content to you. Each one of those collaborating computers has its own IP address. Different schemes, for example, HTTP and HTTPS, use the network in different ways in order to get the information to you. As a result of Edward Snowden's release of top-secret US information, an industry-wide upgrade of security protocols was prompted in order to encrypt data on the internet, on the network, by default. Let's talk about some of those things. So our motivation for this is that generally when we think about the internet, we think about it in a very abstract way. We have some sort of client, for example, a smartphone or a laptop, desktop computer, and we have some sort of server out there, for example, a web server, that's waiting for us to request information through a URL or an internationalized IRI, and then to have that information returned back to us. In between, the internet exists like this cloud of magic computers that we don't think much about, represented here on the slide by a blue cloud. And what I'd like to do is I would like to think about this cloud in a little less abstract manner, especially as you get into the process of working with networks and developing programs that use the network. Being able to understand where problems are happening in the network is important. And to do that, you must have an accurate understanding of how the network is operating. So here's a less abstract version of the internet. This is an example of the actual computers that are contacted as I made a request from Westmont College in Santa Barbara to the University of California, Irvine in Irvine, California. In order to make this request, a total of at least 15 different computers had to collaborate together in order to get my request from one campus to another campus, and in order to pass the resulting returned data back from UCI to Westmont. Well, which computers were contacted along the way? Well, 1, 2, 3, 4, and 5, the first 5 computers that were contacted, all belong to the Westmont campus. And you can see that the second one, at least, uses an IP address of 10.110.111.5. You may recognize that as being a private IP address, reserved for organizational domains that's not visible to the greater internet. So this step number 2 existed behind an organizational firewall. That firewall probably was step 5, the point at which my traffic left Westmont's campus and was delivered to a commercial network called Quest. Quest carried my traffic for 3 more steps before it passed it on to another company called Level 3. Level 3 passed it on to Scenic, and Scenic ultimately passed it on to the UCI firewall, step number 14, called Khazad Dum, which is a Lord of the Rings reference for those of you who are interested. Those 15 steps all were working together in order to get my data from one place to another. That's interesting. So my request started here. There were more than one paths for me to get my request to the destination. The internet worked together to choose one. My data was sent over and the web server received it. When the web server returned a reply, it may or may not take that same route. Each time data is routed across the internet, a new route is potentially established based on traffic conditions, whether or not computers are currently working or not working, and sometimes a little bit of randomization. So now the underlying mechanism for getting traffic from one place to another can be thought of in 2 different ways. You can think of this as TCP/IP or UDP. Now what we're talking about here is the equivalent of like the US Postal Service. We can think about a physical letter that we would like to get from one place to another, and we might be able to choose different carriers. For example, the US Postal Service, or maybe FedEx would be an alternative. In this case, there are 2 different mechanisms for getting content across the network. We can use TCP/IP. From a software perspective, what's interesting about TCP/IP is that whenever you send a packet, TCP/IP guarantees that it gets there. And if it doesn't get there for some reason, for example, one of the computers in the middle of the path loses it, then the client will resend that packet again and again and again over TCP/IP until the web server acknowledges that it received it. On the other hand, there's a different kind of system called UDP. Maybe this is a little bit more like FedEx. And UDP works in such a way, from a software perspective, that if packets don't make it to the web server, they're just ignored. They're not resent. That's appropriate for things like watching streaming movies or listening to streaming music. Because that listening experience or that viewing experience depends on timely receipt of data, if a packet is not received at a given moment in time, for example, a few notes from a song because you have a bad network connection, those packets aren't resent because by the time they would arrive, the music has already been played and it's not helpful. So TCP/IP guarantees that information gets from one place to another. UDP uses the same routing technology but doesn't resend if necessary. It's kind of like the post office or FedEx for deciding whether or not you want to get something from one place to another, except that that's a choice between carriers, and neither of those carriers is expected to drop your letters along the way. Now, from here on out, we're going to kind of assume that we're working with TCP/IP because most of the ways in which we're going to talk about routing assume that our packets are getting to their destination. So one protocol that we can use on top of TCP/IP is something called HTTP. Now this is a little bit like the letter that you choose to send through the post office or through FedEx. We're going to choose to send this letter through TCP/IP. HTTP stands for Hypertext Transfer Protocol. And one thing that's notable about it is it's not encrypted at all. All the information is passed from all those 15 computers all the way to the web server, and any one of those 15 servers is able to read the information that's in that packet. This is like sending a postcard through the mail. Any carrier that picks that physical postcard up and looks at it can read the contents of the postcard, not hidden. We can also talk about the scheme HTTPS, or Hypertext Transfer Protocol Secure, also sent over TCP/IP, but in this case, all of the requests are encrypted. And so this is a little bit more like a physical envelope. In the same way that an envelope has the destination address and the return address, information that's sent using HTTPS also identifies where it's going and where it came from. But the contents of that packet are encrypted, just like an envelope is sealed. And even though a postal carrier can tell where the letter is supposed to go, they can't, without breaking into it, look and see what's in the content of the envelope. Same with HTTPS. Now, when you use HTTPS, there are a couple different flavors that you can use. You can think about this as different kinds of envelopes that you might send your data in. The state of the art is called TLS 1.3. Although all versions of HTTPS send encrypted packets, TLS 1.3 uses something called perfect forward security, which means essentially that each packet has its own password. And if someone were able to break the encryption on one particular packet that's being sent, it wouldn't help them break the encryption on any of the other packets. This is currently state of the art. So what are some tools that we can use in order to reveal the path that data is taking from an origin to a destination? Well, one tool we can use is called traceroute. Traceroute is a command that's run on the command line and will help you identify what the path looks like between two locations. The way this works is that traceroute issues 3 queries to each one of the computers along the way. Those queries may reply with their identity or they may not. And if they choose not to reply, either because they've been configured not to reply or because the packet was lost, traceroute will report an asterisk. When the node in between returns back identifying that it's on the path, traceroute will try and look it up in the domain name service registry in order to understand who owns that particular IP address. Not all IP addresses along the way, however, will have a domain name associated with it. Each of those 3 queries possibly could take a different route because there are many different roads that you could take from one origin to one destination on the internet. And since traceroute doesn't know how long that route is when it starts the process, if it gets to the last node and the last node, for whatever reason, chooses not to respond, it's going to continue thinking that the path is longer and longer and longer, but that those nodes are not reporting because it never receives a response from the destination, either because of dropped packets or because of misconfiguration. So let's take a look at one particular path. This is the path that I used in the beginning to demonstrate. Using traceroute and looking for the route to www.informatics.uci.edu, you would issue a command line command that's traceroute, www.informatics.uci.edu. The computer will proceed to start interrogating the network. You'll see, first of all, there's an IP address lookup that's listed on the first line. And you can see also that at the end of that, there's going to be a total of 64 intermediate nodes that are going to be tested. If you get to more than 64, then traceroute's just going to give up, saying something's gone wrong. As we look at our first node there, you can see that 3 different packets were all routed through the same server. You know they were routed through the same server because only one server name is listed, 10.45.63.254, whose domain name is gw45v1.westmont.edu. The 3 packets that were routed through the network returned with a time. It took 1.085 milliseconds for the packet to get there and return, and 0.594 milliseconds for the second one, and 0.750 milliseconds for the third one. So you can see there was some variation in the amount of time, probably dictated by network congestion along the way. The second path ended up at a computer. The second node was a computer whose IP address was 10.110.110.5, notably within the private address space, so likely behind a firewall on the origin side of the firewall. In this case, there wasn't a domain name to look up, and so only the IP address was revealed. And you can see that 3 different queries all made it through this route, and these were particular fast queries. Each one of these queries was faster than the average time of the previous query. As we get down to the 7th example, the 7th node in this network, you can see that actually the packets that were sent to the 7th node ended up at 3 different nodes for the 7th step. Different routes were taken, in particular on the Quest network, and each one of them had a different response time, 8.755, 12.396, and 8.486. This reflects some of the variation in the path that you might have as you're sending information from one place to another. Just a normal part of the way the internet works. Step 8, you can see that one of the packets was lost or dropped or not responded to by the server. That's represented by a single asterisk. The domain of the 8th step is reported there along with 2 times following it for the 2 packets that were not lost. On step 9, you can see that the server did not respond at all, either again because the packets were lost or because the server chose not to respond. What we're going to see is that there was a lot of congestion on steps 8 and 9, and they were probably lost in transit because there's too many packets for steps 8 and 9 to handle. We'll see that in a different tool. Finally, you can see as we get down to step 14, we hit the UCI firewall. No other servers responded after this one, which is what you would expect from a firewall. You wouldn't expect that someone outside of a firewall would be able to query computers inside a firewall. And so the firewall responded, but all the servers afterwards never responded because the firewall didn't allow that to happen. So 15, 16, 17, all the way up to 64, all replied with 3 stars because traceroute didn't know when the end point of the network was reached because we never had a response from a computer that resolved its name as www.informatics.uci.edu. Interesting, some of the things you can learn along the way. Another tool that we can use is called MTR. This one typically has to be run with the sudo prefix, allowing the utility to have system-level administrative access. And we use -T in order to provide this real-time update about how the information is being routed. What we see when we run this command is not just 3 queries, but a continual set of queries that are being issued to all of the steps along the way. In this case, looking at the column marked SNT for sent, it says that we've sent out 21 packets to all of the first 12 nodes, and 14 we had only had a chance to send 20 when I grabbed this screen grab. And there's a lot more information that's being displayed here. For example, the column that says loss. You can see that steps 8 and 9 are losing 80 and 90% of their packets respectively. Something is going wrong in the internet in steps 8 and 9 here. This is probably just a temporary traffic bottleneck, probably will resolve itself fast enough that a user wouldn't even notice. But we do notice that of the 21 packets that I sent, 80% and 90% were lost. You can see 1, 2, 3, 4, 5 different columns then related to the timing of those packets. You can see how much time the last packet took, what the average amount of time that the packets that had been sent took, what the fastest or best time was, what the slowest or worst time was, and then what the standard deviation was of all the times that have been collected. So overall, this gives you a very dynamic, real-time picture of how the internet is changing or evolving as you're watching the path between 2 destinations. If during this process we had seen multiple nodes respond as we did previously for step 8, then what we would see is we would see one of these rows would have multiple entries in it for whatever number step it's on. It's pretty straightforward to understand when it happens, if you know what to look for. All right, so in summary about evaluating these schemes, if you ever have an IRI, internationalized URL, that starts with HTTP and is followed by any domain name, that content is going to be insecure. All of the computers that help to deliver that content or respond to that content are going to be able to read the content that's sent in transit. So your bank information, any insurance information, information about whatever Wikipedia page you're following, all of that is completely visible. In contrast, if you send a request using HTTPS, you have a secure connection between the origin and destination. The computers along the way can't tell what's being sent. There are several different levels of security, however, that you as a user of a web browser don't necessarily know which one you're using. TLS 1.0 and 1.1 provide moderate security. This is not perfect forward security. So if you're engaged in a communication using HTTPS and the resources are put to bear to try and break your password, it will be sufficient to understand all the content of your communication, regardless of how many packets are sent. Starting with TLS 1.2, perfect forward security was introduced so that a single break of a password wouldn't be enough to understand every single communication that is being taken between the origin and destination. And finally, TLS 1.3 is state-of-the-art security with high-grade encryption and high-grade cryptographic procedures. How might you know what a web server is doing with respect to its security? Well, you can use an online tool, among other things. Here's one that I kind of enjoy looking at. It's from SSL Labs, and it will provide an evaluation of a website that you enter in through a web-based interface. So I asked them to do an evaluation of a few different websites, and you could do the same. It takes a little while to run, and they'll look at a bunch of different vulnerabilities and the different levels of security. So evaluating UCI.edu, SSL Labs gives UCI a B. This is probably because the TLS versions 1.2 or 1.3 are not enforced by the destination. Now, this is not necessarily the worst thing in the world because a communication with UCI.edu, while you would like that to be secure, maybe doesn't have to be super high security. And as UCI upgrades their website or as the standards change, this grade may go up or down. Let's take a look at Westmont College's grade. Westmont, for similar reasons, also receives a B. How about MIT? MIT.edu, Massachusetts Institute of Technology, does a little bit better. They receive an A grade. High encryption, high security along the transit. What about the NASA website, the U.S. Space Agency for the United States government? Well, fortunately, that's an A+. And that's something that we would hope to see in highly sensitive websites that potentially provide highly sensitive data, that they would have maximum security. Now, some frameworks that you work with, some programming environments, won't allow you to access resources on the internet through international RIIs, internationalized URLs, unless you have sufficient security. For example, not too long ago, iOS native apps began requiring web servers that they communicate with, that an iOS device communicates with, to have TLS 1.2 installed by default. And any website that wasn't using HTTPS at the level of TLS 1.2 couldn't be used for data exchanges. This would be the kind of data exchange that happens between a native app, like maybe the Instagram app, and the Instagram server. Different than a web browser, but still using the HTTPS protocol back and forth in order to exchange information. Now, this is a little bit nuanced because there are ways that you could downgrade this requirement if necessary, if the web server couldn't be upgraded or for some other reason. But basically, an application has to be high security in an iOS environment, a native app. Browsers, a special class of applications, are an exception. Whether running on a desktop or whether running on a mobile device, typically browsers will use the highest level of security possible, but will downgrade if the web server doesn't support that. For example, most modern browsers support TLS 1.3. But if you're communicating with a website that only supports TLS 1 or 1.1, then the browser will downgrade and use a lower level of security because the web server can't support anything higher. Some websites, in order to encourage and promote security, will not allow you to connect to them with HTTP. Increasingly, this is the standard. It is harder and harder to find websites that will respond to HTTP requests. Some web services will automatically upgrade to HTTPS. For example, the web search engine DuckDuckGo does this. If you access them with HTTP, they will upgrade their security to HTTPS. Let's take a look at what this looks like in a browser context. We type in HTTP DuckDuckGo, the response goes out, and the server immediately redirects the client or the browser to a higher security web page. Is this good? Well, this isn't good in some cases. In the browser case, this is great because you would like to have a higher security connection and have that applied automatically. But if you are a native client and you're communicating to a web service and you're using an HTTP request, for example, this HTTP request here, http://api.service.com, access token equals 039450, the assumption here being that the access token is something secret or something that shouldn't be revealed to the rest of the internet. When this first request is made before the redirect, all the computers along the way have the ability to see the access token, like a postcard being sent through the postal mail. That's bad because you've had secure information released. And even if the next connection upgrades to HTTPS and future traffic is encrypted, you've already revealed the secret information that may have compromised your communications channel. So what's the takeaway? Basically, don't use HTTP. And make sure that within your code and within any sort of protocols that you have set up, you don't rely on a redirect. You always use HTTPS from the beginning. Okay, so to summarize, when you request an IRI, an internationalized URL, when you request a web page, for example, from another server, many computers have to collaborate in order to deliver that information to you. All the nodes on the path from the origin to the destination. Each one of those computers has its own IP address, and in many cases, they also have a domain name. Depending on which scheme you use, HTTP, HTTPS, the network will be utilized in different ways, including the TCP/IP or UDP underlying technology. A lot of the security has been upgraded by default recently, and that's a result of Edward Snowden's release of top secret US information, which ultimately prompted the industry to use high security communications by default. I hope now when you put a request into a web browser and you see a little bit of a delay or you see differences in times between one request and another request, this gives you a little bit of appreciation of the underlying infrastructure that's working to deliver this content to you. It's a complex and, in a way, kind of aesthetically beautiful process in which we connect computers across the internet. Thank you for your attention.